Welcome back. Still working on radius and interval of convergence for power series. We're going to keep on with a couple of examples, and before I mentioned we can sometimes have the radius equal either 0 or infinity. We want to see when that arises here, so we're going to do a couple examples, test this out. We won't worry about the interval right now. We'll find the radius r for this power series, n equals 0 to infinity of n factorial x to the n. Now, a little thing to note here, just in the way it's written, usually we have x minus a to the n in the power series form, and this just means if it's x to the n, your a is 0 here. That'll become useful later on. The other thing we want to notice, the cn's here are n factorial, and we know that n factorial grows very, very quickly relative to other types of functions, even like exponential functions. So this one, I'm thinking that it's going to be really hard to make this converge for any x values because of the way in which the coefficients are growing so quickly with n. So we're going to test out what happens with the ratio test here and see what it says about r and how we can interpret that statement about L in this new context. Okay, so of course, the only test we ever use for a radius and interval of convergence is the ratio test. So set it up. Limit n to infinity an plus 1 over an n plus 1 factorial x to the n plus 1. Now this one actually, unlike most of these expressions, this one doesn't involve a denominator or a ratio of two expressions. So I can just literally do my an plus 1 over an without too much bother here. It's just as such. Absolute values on the whole thing. We've seen this a bunch of times now. The n plus 1 factorial over n factorial just gives me n plus 1. And I have an x to the n plus 1 over x to the n. And so that's n to infinity now. Of n plus 1, and then this reduces down to just the absolute value of x. Now, you might look at that and say, well, as n goes to infinity, n plus 1 goes to infinity. But I want you to stop that tendency for just a second. We're going to hold off on this. I'm just going to rearrange this, pull my x outside of the limit expression, and just condense down the limit as n goes to infinity of n plus 1. Now this limit is definitely equal to infinity. As n goes to infinity, n plus 1 definitely goes to infinity. But what I'm going to do is just to carry this through in a similar format as to the previous question. I want to basically associate this with the statement x minus a less than r. So I'm going to write this in a particular way. I'm going to go x infinity less than 1. Now this is the condition, the ratio test condition for convergence. This is like the L. And if you think about it, I mean, if you're multiplying any x value by infinity, you're not going to be less than 1 except for one specific value of x. But what I'm going to do is this. I'm going to leave that infinity as though it were a number, and even though it isn't, I'm going to write it as 1 over infinity. Now 1 over infinity represents, in some sense, the idea of 0. So this, another way to write this would be x minus 0, and I'm only writing that in just so we can recognize the format, less than 0. So I've left the infinity, and just to recap here, this infinity, I've left it as a number and divided it over here, and then interpreted 1 over infinity as 0. Now the benefit of this is I'm comparing this statement that I obtain to this statement. This statement, if I can massage my expression into this statement, what it gives me is a way to match up the terms. So here I get a is 0. I already knew that. But more importantly, here I get r equals 0, just by kind of matching up to that form. So that would be my suggestion when you hit a term that does go up to infinity, like this All right, leave it as infinity in your expression, divide it through, and then you can reason out how the radius is 0. So anyway, we found for this particular series then at x equals 0, right at that point it converges. Every power series will converge at the value x equals a, but then you step immediately off that point and you diverge. Like that. All right, so only for a single point does this power series converge at x equals 0, which is the a value, and then because of the 0 radius of convergence, stepping immediately off of that value, you will diverge. All right, let's try one more. Consider the series n equals 0 to infinity. I'm going to go -1 to the n, x to the 2n, all over 2n factorial. Okay, so let's hammer this the same way. We got the ratio test on board. So we formulate our expression, the limit as n goes to infinity, an plus 1 over an. Okay, so n's going to infinity. An plus 1 is -1 to the n plus 1. Inside the absolute value, so that's always going to be 1. X to the 2n plus 1. Use your brackets. Don't make that 2n plus 1. That's not right. Okay, it's 2 bracket n plus 1, which expands out to 2n plus 2 when you do it. Similarly down here, it's 2n plus 1 factorial. All right, so there's the first expression. Then I'm going to multiply by the reciprocal, giving me 2n factorial, -1 to the n, x to the 2n. Absolute value around all that. All right. Now, I'm going to just basically, since they're inside the absolute value, that and that I don't need to keep track of. They're just 1. -1 or 1 in absolute value is always equal to 1, so I'm going to get rid of those two things. And then I'm going to group like terms like I have been doing before. And so I have, if I look at my factorial terms, I've got 2n factorial, 2n plus 2 factorial. And then remaining, I have an x to the 2n plus 2, when I expand that out, over an x to the 2n. Now all the x stuff can be reduced down to just x to the power 2. So we're getting there. This is 2n factorial. This is 2n plus 2, 2n plus 1, 2n factorial. Okay, so those are going to cancel. And then I'm left with an x to the power 2. I'll bring the x stuff outside, and I'm left to evaluate the limit as n goes to infinity of 1 over 2n plus 2, 2n plus 1. All right, and so as n goes to infinity, that numerator is stuck at 1, the denominator is growing, so I get 1 over something getting larger and larger and larger as n goes to infinity. And so that becomes 0, 1 over an increasingly large number. And again, you might reason, well, that just means the whole thing is 0, so there's not much to do here. But again, I urge you to continue on in the same process as though it was a finite number like we found in the first example last class. So I'm going to go less than 1. Again, I'm imposing this condition. Condition for convergence. The L has to be less than 1. And again, I just want to push this into the form of x minus a less than r. And then, as such, I divide 1 by 0. Now, 1 over 0 I interpret to be infinity. And if my x squared is less than infinity, well, if I take the root of both sides, I get x less than infinity. And I'm just going to make a little note. The root of infinity is also equal to infinity. Doesn't really make a difference. All right, so at the end of the day, I've got this statement here, and again, from this, I can say a is equal to 0. I knew that starting off, but now my r is sitting here as well as my infinity. Okay, so this one happens to have an infinite radius of convergence. So here r is equal to infinity, and so as soon as I get that, I always know my interval goes from minus infinity to infinity. Doesn't matter what the a value is. My interval covers all the numbers. And so that leads, that was the third case, and so we have 3 outcomes. We can go x minus a less than r, where r is finite. In the very first example we saw this. Okay, so this is some non-zero number. Then the interval of convergence is a minus r to a plus r. I think in the first example it was a half. Okay, or we can get x minus a times 0 less than 1. We just saw that in the last example. In this case, I go x minus a less than 1 over 0, which I interpret to be infinity. My r is then equal to infinity, and my interval is all real numbers. The third thing that can happen is I get this x minus a expression multiplied by infinity, and I bound it less than 1. So then I go x minus a less than 1 over infinity. I interpret that to be 0. And here my r is 0. And my interval is just simply a. It has no width. It's a single point. All right. So there's one other consideration. I'm going to get a new sheet up here. Before we move along, one more consideration. So we've been talking about, I'll draw for the finite case. We have some a, and then we have a plus r, a minus r, and we're calling this span here the interval of convergence I. Now, anytime we talk about a range of values for which a series might converge or diverge, we have been implicitly assuming that we're not including those endpoints. We've been using round brackets in our expressions. So I don't actually know what the answer is, but it is a question, what happens at endpoints? And it turns out that it may converge or it may diverge, but we can test that. So we must check these endpoints to see. Now in practical terms, do you always have to check the endpoints? You don't if I don't ask for them. But if I wrote a question saying, also check the endpoints for convergence, then you'd have to go do it. All right. So let's do a little example. I'm going to go with the sum n equals 1 to infinity, and note, starting at 1, that's okay. It just means the very first term is going to be 0. So you can think, hey, C0 is equal to 0, and that just starts my series at 1. It's still a power series, no problem. The reason why I'm doing that is I want to write my terms here, including an n in the denominator down here, and I just want that to be properly defined. Okay, I'm going to go x minus 2 to the n. So I want to get the radius and interval and test the endpoints. Okay, so I'm explicitly asking for that test to be done to check whether or not those endpoints exist inside the interval of convergence. Well, I've only got one tool to use. It's the ratio test. So limit n to infinity, an plus 1 over an. An plus 1 is minus 3 to the n plus 1, x minus 2 to the n plus 1, all over n plus 1, absolute value, multiplied by the reciprocal. There's n minus 3 to the n, x minus 2 to the n, absolute value. All right, now we stack up like terms in this expression. And by that, we see a minus 3 to the n plus 1 over minus 3 to the n. Consider those together. Now, I do need my absolute values here because minus 3 to the n plus 1, or n, is going to waffle back and forth between positive and negative values. I've also got an n over n plus 1. Don't really need absolute values there as they're all positive. And then I'm left with an x minus 2 to the n plus 1 over x minus 2 to the n, which we've seen a few times now. It's just x minus 2. All right. Now, minus 3 to the n plus 1 over minus 3 to the n is the same thing as the root, or sorry, the absolute value of minus 3. And so I just get a 3 out of that. I get an x minus 2, and then this n over n plus 1. Or pulling out the things that don't depend on n, I'm left with the limit as n goes to infinity of n over n plus 1, which we've seen before, right? This limit is definitely equal to 1. Okay, ratio of leading coefficients, however you want to determine that, that limit is equal to 1. So I end up with 3x minus 2 times 1, and then I go less than 1 in absolute value, the condition for convergence. So I apply the convergence condition for the ratio test. And so what that does now is allows me to go, all right, x minus 2, there's a 3 there, so I'm going to drag it to the other side, make it 1/3. And I'm done the first step of this. There is my a value, a is 2, there is my r is 1/3. So using that, I can formulate my interval now, I as a minus r, a plus r, and I'm using round brackets at this point because I don't know whether the endpoints are included or not. That's 2 minus 1/3 and 2 plus 1/3, or I can say, I guess that's, what's that, 6 over 3 minus 1 is 5 over 3, and then if I add a third on, I would get 7 over 3. All right, so now that's the first step done, and now I check the endpoints. I'm going to show you how this works. It boils down to basically a simpler problem that we would have dealt with earlier on in this material. So I'm going to first try let x equal 5 over 3. And I'm going to go back to my original series. And simply plug in x equals 5 over 3 into that expression. Okay, so just to remind you, the original series is right up here. Okay, so that thing is going to get the x value placed into it as a value of 5 over 3. That's going to give me all numbers here, okay, and that's going to reduce this down to basically a summation of some an. There's not going to be a variable x in it anymore. So it kind of reduces back to just one of our generic test for convergence problems that we would have done a while back now. All right, so let's see what we get. The sum, n equals 1 to infinity. Remember the first term was 0. Minus 3 to the n. 5 over 3 minus 2 to the n. That's all over n. A little bit of math required now. So I have minus 3 to the n. 5 over 3 minus 2 is equal to negative 1/3 to the n. And that's all over n. Now, if I have two different bases here to the same exponent, I can combine this all as the product of the bases to that exponent. That is to say, I can write this as minus 3 times minus 1/3 all to the power n. That's over n. Now minus 3 times negative 1/3 becomes a 1 to the n, all over n. Now 1 to the n, doesn't matter what n is, that's always going to be 1. So this all boils down to the series 1 over n. And this thing, immediately I know it diverges because p is equal to 1. It's a p series with p equals 1. And that diverges. So I need not do anything else. I've already figured it out for that 5 over 3 value. Leads to a series that right at that point, it's going to diverge. Let's try the other one. Let x equal 7 over 3, and we'll see what happens here. So it's the same process. We take our series and replace x with 7 over 3. And then we do a little bit of math to simplify this and see if we can determine the convergence of this series. 7 over 3 minus 2 is 1 over 3 to the n, that's over n. And this becomes the same way, minus 3 times 1/3, that is all to the power n over n. And now we get something slightly different, you might notice here. You get minus 3 times a third is minus 1 to the n over n. Now, it's been a little bit of time here, but this is an alternating series because of that negative 1 to the n term. So we use the alternating series test, which has the an being the non-alternating part of 1 over n. And we check two things, that the limit as n goes to infinity of an has to go to 0. Sorry. But it definitely is. As n goes to infinity, 1 over n goes to 0. And then the second thing, it has to be strictly decreasing, so an plus 1 has to be less than an. But of course, 1 over n plus 1 is less than 1 over n. So by the alternating series test, this series converges. So that was at x equals 7 over 3. So here's what we've done, just to recap here. We've got a value of 2. That's the a value. We went out of an r value equaling 1/3, right here. And that got us up to 7 over 3 and down to 5 over 3. This whole thing here is the interval of convergence. Okay. Maybe I'll just mark it like this. The interval of convergence, like here. And then we checked specifically right here and right here. And we said at 5 over 3, the expression, the series that results, it diverges. And over at 7 over 3, that led to an alternating series, which we could show converges. So finally, we use all that information together, and we say I, the interval of convergence, is 5 over 3, not including the n boundary, so we use a round bracket there, and 7 over 3, including that boundary, so we use a square bracket there.